Hello everyone, Trevor May, VRF Ductless Split Technical Specialist here, back for another Tech Tip mini-series. On this Tech Tip mini-series, we are going to focus on the P0 error code. Now, when we say the P0 error code, we're referencing troubleshooting that from our indoor unit. So with the P0 code on there, the P0 code is in reference to an IPM or IGBT. Okay, so the IPM is an intelligent power module. Essentially, it's our compressor drive board. You'll hear these boards often referred to as either a compressor board, a drive board, and IPM. There's a lot of different names that are associated with what that board is. But essentially, understand we're talking about the same thing. We're talking about that inverter drive. Okay, and of course, the IGBTs are the pulsating switches that pulse that DC voltage to the WV switch compressor, and also for the outdoor fan motor, of course, depending on your outdoor setup. But what this code is specifically looking at is saying, hey, we have an issue going on with the IPM board, but it's not that cut and dry. There are a lot of intricacies on what can and also what can't cause this code. Now, of course, just like on previous tech tips, I'm always going to refer you to the flow chart, especially if you're just starting out with this code. So it's going to get you a nice foundation of where you need to be, and also some things that you can test on a basic standpoint before really reaching out for technical support and building your knowledge of troubleshooting various codes on ductless systems. Again, as I always state in the tech tips, the flow charts are a good source of information to get you on the right path. If you follow these word for word, you're going to end up replacing an outdoor fan motor, a board, a compressor, and the issue's still going to be there. So it's important to not exactly follow everything that that flow chart is telling you, but it's certainly something that can guide you in the right direction, especially if it's a code that you're unfamiliar with. One thing you'll notice about this slide on here in red, I have a little reminder on it. Again, this was more so discovered from my time in the field and also some experiences I've had with certain contractors and issues that we've had with this code. So as we go through the troubleshooting process, if we've gone through everything on there, the last step in the process is we want to make sure that we're checking each wire to ground. I have seen this issue before where the faulty wire is causing an issue with this PO code that's feeding back directly to that drive board. So again, just like with any other code, don't assume that it's a board. It's very rare that we run into failed boards unless it's from an external issue, such as a power issue or something with a shorted part. Again, don't assume it's just a board. That should be your really last focus in your troubleshooting process with inventing the board, unless you can actually visually see that something is burned up, and of course you want to verify what caused it to burn. So when we're going through and we're troubleshooting this PO code, the first thing that we want to do on here is we want to access where this board is. Now, certain model units offer a different level of difficulty depending on how you need to access this board. On the left side, that's a representation of our multi-zones where we have two split boards, so a main PC board, power and communication wiring that connect the main PCB over to your inverter drive. Now you'll see on the inverter drive that you'll have these three terminals on here, and they're E1, E2, and E3. And on this board, it's pretty straightforward. It has your positive and negative posts that stick right out of the back side of the board, and this is what you should be seeing. Now what these are, if you look at the circuitry of the board, you'll see there's three little circles that go around the positive and negative post where the E1, E2, and E3 terminals are on that board. That is the underside or the access point of the capacitors. So not only for the terms of testing, the IPM's continuity, which we're going to go through here in a second, but also verifying your incoming AC voltage. So if you look to these picture on the left, you'll see these two terminals right up here, either L and N. So that's your incoming AC power, which is taken from the main PC board. So if you're trying to troubleshoot a board or troubleshoot if something is getting funky inside of this board, you can always take your meter, set it for AC voltage, and go between these two terminals. And you're looking for line AC voltage. Now, if you follow this down through here, you'll notice you'll see this little diagram right here. That is our bridge rectifier. That's where we take this incoming AC voltage and rectify it over into DC voltage. Okay, so that's where that's happening right there. Now, one thing we can troubleshoot is, okay, I have the correct power in, but am I getting the correct power out for DC voltage? buses because that's going to be next in line aside from the reactor on there, which we know is that filter, which essentially cleans up that newly generated DC power. Okay, so what you can do is you can verify your incoming AC voltage, of course, plus or minus 10%, and then go over to your DC side, and you want to go and set your meter for DC voltage and go between the positive and the negative posts, and you want to confirm that your DC voltage is correct on there. Now, when you're checking for DC voltage, it's always a safe assumption to assume whatever your incoming power is, your DC voltage will be typically about 1.4 greater than your incoming AC voltage. So for example, if you were going through and checking your incoming AC voltage and you measure 232 volts AC, what you should expect on the DC side should be that 232 times 1.4. That number should be what you should expect on your capacitors for your DC voltage between your positive and your negative post. Okay. If you have a higher incoming voltage on the AC side than you do on the DC side, so let's just say, for example, you have 232 volts AC, you only have 210 volts DC on the capacitors, you have an issue with your bridge rectifier, which we know is being right here. It's internal to the board. You can confirm that. You've seen it through a voltage reading, so you know to replace the board because the bridge rectifier is in the board itself and it's not external to the board. Okay. So that's just one thing on a basic troubleshooting point of view that we can roll out. Are we getting the correct AC voltage out? Are we getting the correct DC voltage out? Okay. So let's stay on track here. Let's go through this IPM continuity check. So we know about our capacitor buses. We have a positive and a negative post. Now the next thing you'll notice on here are your three terminals that go directly to your compressor, which are your W, V, and U terminals. Now what we're going to do is we're going to go ahead and shut the power off to the system. Give it 5 minutes, allow this capacitor to discharge. We're going to take our meter, we're going to set it for megohms on there, and then what we're going to do is go between the positive and the negative post for megohms. Okay, we're going to go between the positive and the W, the positive and the V, the positive and the U. We're going to go down to capacitor E2, do this exact same thing, positive, negative megohms, positive to W megohms, positive to V megohms, positive to U megohms. Do the same exact thing on the final capacitor, which is E1. Okay, positive to W, V, and U, and then we're going to do the same thing with negative to W, V, and U. And this is going to ensure from the time that we leave our capacitor buses until we get to our IGBTs or pulsating switches, that we have a good electrical circuit. Now, you'll notice on the chart on the upper right-hand corner of this slide on there, it says several megohms. Typically, I tell guys about 5 to 8 megohms is acceptable. If you're getting readings of 25 or 30, or if you're reading open, you've just confirmed that you do not have a complete electrical circuit and that there is a backing issue within that drive board from the capacitor buses up to the IGBTs where there's pulsating switches out to the WV and U terminals, which go directly to the compressor, which will confirm why you're getting an IPM drive board. Now, in this case, of course, if you confirm that, then you know that there's an issue with the board. You can't make that assumption just based off of, well, I'm not sure what the board does. I don't know how to troubleshoot it, so I'm just going to replace it. This is a fundamental way to break this board down, to understand how the voltage is going through it, how it changes from AC to DC, and where it actually goes throughout the circuitry on the back side of the board. So that's going to be one of the biggest things that we want to check, but that's not going to be the first thing that you want to check, but it's certainly great knowledge to have. Now, we looked at it on the multi-zone cell system, which is on the left side of the screen. Now let's go over and look at it on the single zone cell or the single board system on the right. Now you'll notice this one because it only has one board. This is typically on our smaller single zone units, such as the 9, 12, and 18, where we have a single board, where it's a main PC board and an inverter drive in one. And you can always tell that because, well, one, there's only one board, and two, there's a heat sink connected to that board. That heat sink is essentially a way for those IGBTs or those pulsating switches to reject their heat so that board does not overheat. That's oftentimes why you'll see these boards face down and in the condensing section. So when that fan motor is running, it's passing air through the fins of that IG or the actual heat sink itself, so they can get rid of that heat. If that gets clogged up with dirt Or if something's not working properly with a thermal paste that actually from the heatsink to the board that's in there, if you don't put thermal paste on there, like if you go to replace a board and for some odd reason you have to take the heatsink off of the older board and put it on the new board, and you don't use thermal paste, it can't properly transfer the heat from those switches opening and closing in order to heat the board and take off on this code. So again, something to keep in mind on there, and also something that you should be checking on maintenance for the actual heatsink itself to make sure that it's not compacted with dirt, so that air can freely flow across the heatsink to properly remove heat from the board when those switches start pulsing as they do generate a lot of heat. Okay, but on the single zone cell boards, you'll see you still have the same setup, but it's not as straightforward as the board on the left. But what we are looking for are those three little circles on the board on there, which are an indicator of the backside of your capacitor, E1, E2, and E3, just like we did on the left-hand side. And you'll see on here, your positive and negative posts. Okay, so that's where you want to check for that DC voltage on it. Same rules apply. Whatever your incoming DC voltage is, multiply that by 1.4, and that should be the DC voltage reading that you should expect across these capacitor buses. Now what you want to look for on there is where your compressor terminals, so your WV and U, come to the board. And you'll notice they're not labeled on here, so it can be a little bit difficult to make sure that you have the right terminals. What I suggest that you do is open up the front side of the unit, follow your compressor wires up to the board, and see where they plug into. You want to look on the opposite side of the board of where those terminals plug in, and you can confirm that would be your W, V, and U. Now in this case, you can see down here, this is where our W, V, and U terminals are. And this is where capacitor 1, capacitor 2, capacitor 3 is located for the positive and negative terminals. We're going to do the exact same thing. We're going to go and take our meter and go between P and N. We're looking for several megohms. Then we're going to go from the positive terminal on capacitor 1 to WV and U, capacitor 2, WV and U, just like we did on the other board to troubleshoot. Same exact thing, just visually a little bit different depending on the type of operation that you're dealing with. Single zone, multi-zone, and of course in the single zones, the tonnage. So here are some things that you definitely want to look for when a PO code is active. Now what we talked about before with checking the continuity on the board is certainly something in good knowledge to have, but it shouldn't be your first step in that process. First step when you start troubleshooting this code, you should be confirming your incoming volts AC reading on your bus bar, which you guys know the plus or minus 10% rule, 187.2 minimum, 253 volts max. Typically, if you're over that 253 on your incoming side, or you're right at that threshold, you should kick off on an over voltage code, but of course we don't live in a perfect world and it doesn't always necessarily happen. Now one thing to keep in mind on there is we want to check that output volts DC on that capacitor bus that we talked about before between the positive and the negative terminals. Okay, highlighted in red, 357 volts DC is the absolute maximum that we have. If we go over that, the unit will throw a PO code, which is that IPM, malfunctional protection. Okay. Some of the units, of course, it depends on models of what their maximum voltage is, nothing to exceed 357. Some of these will throw this code at 350 volts DC. When we deal with high voltage, this can cause damage to that EEPROM chip, just like we talked about on the main PC boards, which is the brains of the operation, with the algorithm or that set of rules is stored at. That drive board also has one as well to dictate how it's going to pulse those U, V, and W terminals for those IGBTs that go to the U, V, and W. Okay, that high voltage can cause damage to that EEPROM chip due to the excessive heat from the IGBTs and also the excessive voltage, which we know go hand in hand and cause the excessive heat. And in certain cases, I have seen these cause compressor firing issues if the system's been running like this for an extended period of time. Now, that doesn't mean just a month. I've seen it for a couple of days when it's running like this. If you are experiencing higher incoming AC readings to the unit, you always have the option of putting a bucking transformer on there, which steps down that high incoming voltage to a more tolerable level. And of course, we can verify our incoming volts AC and also check our output volts DC to make sure they're within allowable range. Okay, like I said before, On applications where we have a higher incoming volts AC and you're documenting it at 250, 251 volts AC, it may be a good idea, especially if you're installing something, to get your bucking transformer to lower that incoming volts AC down. Of course, if you can confirm that you have a good incoming volts AC reading and a good volt DC reading output, then you want to move on and do that continuity test between the IPM board. So you want to go between your capacitor buses, your W, V, and U. If that checks out, then you can start moving on to other things. You're essentially confirming, is my power correct? Is my inverter drive board working properly? The inverter drive board has failed, or if something surged out and caused it to have a giant scorch mark where your IGBTs are, and of course it's not going to work and the system's going to throw this code. Okay, but if it does check out, both of these voltage readings check out and the board checks out, you want to make sure that you check your wiring between the inverter drive and the main PCB. Now again, this is on a case-by-case basis. If you have a single board, you're not going to have wiring between two separate boards because you only have one. If you have a multi-zone, 18, 24, 36, or 48, depending on what you're dealing with, and the 30 as well. You want to make sure that you are not only your power, which comes from the main PC board, to the inverter drive board, is securely connected, like we talked about before, where I check between the L and N terminals on the left-hand picture. That's where you want to confirm from that terminal to your main board, is that secure? Is there anything compromising those wires? And then, of course, the communication wire. That is a 5-wire plug that plugs in onto that main drive board and the main PC board on it. If that comes loose, or if there's something compromising one of the wires, the boards can't talk back and forth, they can't operate properly, and chances are you'll code out on a P0 code. Typically, this isn't what we run into, but it's certainly something to keep in the back of your head to roll out. If you can confirm that the wiring is correct, continuity test is passed on your IPM or your drive board, and that your voltage incoming and your output voltage is correct, then we want to move on and ohm out our compressor. So what we're looking for ohming out the compressor is a uniform resistance group, just like any other compressor. You just want to go through, you want to see consistency. You also want to double check and take each one of those legs to ground to make sure that the compressor is not grounded. Now, just because the compressor passes the grounding test and ohms it out does not mean that internally there isn't a firing sequence issue when the system tries to start off. That's just confirming, are my coils good? Is my compressor grounded? Okay, that doesn't mean that the compressor checks out, it just passed both of those tests. So we want to make sure that we ohm out our compressor and also check if the ground is verified that it is not grounded. We want to do the same thing with our outdoor fan motor. Again, typically on the split type boards, that's where it's connected to, is on the drive, which is the W terminals, and there are some fan motors that have a 5-wire connection on there. Case-by-case basis. But of course, we're looking for the uniform and the consistent resistance readings across the way and making sure that the electrical connections are connected properly. Next thing I'm going to have you do, if both of those check out on there, is unplug the outdoor fan. Turn the system on to confirm if this P0 code has now mysteriously gone away and another code has reappeared. Technically, if you unplug that outdoor fan motor, you should get a code pertaining to the outdoor fan motor issue, not a drive board error. Same thing with the compressor. You want to unplug the compressor, turn the power back on, see how the system responds. This is also a great way to check to see if your main PC board and your inverter drive board are throwing the appropriate codes based on what you're essentially mimicking. Now, if you continue to get this PO code on there, regardless of what you unplug for temperature sensors, or fan motors, or compressors, you might have an issue with that main PC board throwing a false positive code. Again, this is very rare, but it is something to keep in the back of your head and something that you can proactively do to test them. Unplug components one by one. If you can get that P0 code to go away when you unplug the outdoor fan motor, chances are you probably have an issue with your outdoor fan motor, and vice versa with the compressor. Okay? Again, it's just another tool that you have in your belt to be able to troubleshoot this P0 code. And then if all the above checks out on there and everything seems to be proper as far as readings and what you should be expecting, then you'll have to shut the power off to the unit, and we're going to check each wire that connects that inverter drive board to ground. and also check the pins to make sure that nothing is grounded out, because if it is, it can cause this inverted drive code. Okay. Again, 8 really valuable things you can use as a technician to go out there and effectively troubleshoot this code. Don't assume that it's always a board failure. 99% of the time, the board is the pedal tone system, and it's just alerting you to another deeper issue within that system, which we can use these 8 points here to dive deeper and to narrow down where that issue is. And just like with any code, take your time, don't overthink it, and work the code. Sometimes you need to roll through this process, and that includes myself, to be able to make sure that I didn't overlook something throughout my process. So that's what I have for you guys on this PO code. Hopefully you took something from it. Hopefully you have a little bit more knowledge and insight to be able to approach this code with more comfort. And of course, if you have any issues, questions, concerns, you can always reach out to me. My contact information with number, direct extension, and email is up on the screen. If for some odd reason you need to get a hold of the product manager, both product managers for the ductless and the VRF product line with their contact information. And if for some odd reason I'm out of office, on vacation, or I just can't get to you and you need immediate service, just remember, I'm your first point of contact, but not your only. 3 gentlemen you see here with their extensions listed are in our technical service department, and they're more than happy to help you with any VRF or ductless technical service. Thank you guys for taking the time out of your day to go through this tech tip. I look forward to seeing you on the next one. And of course, again, with any questions, issues, comments, or concerns, please feel free to reach out to me.